Air-operated percussion drills, sometimes called a cluster drill, are typically incorporated into a full-face tool as shown in this photo. Each of the 9, in this case, individual percussion heads in this 66-inch diameter tool are powered by compressed air, which causes each of the heads to hammer away at the rock face. The tool is slowly rotated or moved so that the contact point of each head moves around the base of the excavation. Notice that the drill heads cut a hole that's slightly larger than the outside diameter of the tool and thereby provide clearance for the return of air and cuttings around the outside. You can also see grooves in the bottom of the face to direct the air and the cuttings away from the percussion bits to the perimeter of the cluster drill. The bits are staggered so that as the tool rotates slowly in the hole, the bits do not keep pounding in the same place. Here's a close-up view of the percussion head shown on the left. You can see the center hole where the air flush is discharged and the hardened steel buttons that are used to break the rock at the point of contact. These tools work best on hard, brittle rock which can be fractured by the stress associated with the impact of the percussion head. A softer rock which can absorb the blow without fracturing is not as effectively drilled using these percussion tools. The percussion head must encounter resistance in order to fire and hammer. Otherwise, the air can just flow out of the hammer without working properly. For this reason, a large cluster drill can be ineffective if the rock is not present across the full face of the hole and part of the hole is on rock, part of it is on soil. Besides the great expense of these tools and the wear and the maintenance required, additional expense is incurred in providing the large volume of air that's needed to operate these tools. Several large high-capacity air compressors are required for the cluster drill that's shown in this photo. Similar to the roller core barrel, this cluster drill is equipped with a calyx basket to collect the cuttings. Since the cluster drill is operating on the full face of the excavation, there will be a lot more cuttings than with a roller core barrel. In the photo on the left, you can see the inner casing that was seated onto the rock and a larger diameter outer casing that was used to help contain cuttings that spilled over the calyx basket. These photos are from a project in North Carolina where the foundations were advanced into a metamorphic bedrock in the Piedmont Formation. Here's a short video of the cluster drill operating. Besides the percussion drill pounding away at the rock down there, there's the air flush, which is pretty vigorous down the hole. So it's essential that the hole be cased down to the rock in order to operate such a tool. Without casing, soils or highly weathered materials tend to collapse from all the activity as the hammer drill is working. But this tool is undoubtedly the most effective means of excavating hard rock. The next few photos are from a project in California where percussion drilling was used to advance 7-foot diameter foundations into hard granitic type bedrock. After seating the casing, the rock excavation was advanced in 2 stages. First, a 4-foot diameter hole was drilled using this cluster drill, which you can see in the photo with the calyx basket left slightly open. After the 4-foot pilot hole was completed, a 7-foot diameter percussion drill was used to enlarge the hole down to the required dimension. The calyx basket has been removed from this drill. You can see the short section of pipe in the center, which is called the stinger, that follows the pilot hole and guides the larger tool down the same path. This larger percussion tool is sometimes referred to as a hole opener, which is a common term for any drill tool that is used to enlarge an existing hole. One advantage in advancing the hole in 2 steps like this is that the air requirements for a single pass would be much larger. Also, when the rock surface is irregular, all of the percussion heads may not fire as effectively, so the pilot hole provides an opportunity to see how the rock drills on a smaller tool and sort of explore what you're getting into before you advance with all of the tools in the toolbox. Here's a view down the hole of the 2-step percussion drilling. You can notice that the bottom has a step in it, so the pilot hole had to be drilled a short distance below the targeted tip elevation for the entire drill shaft. You can also see that the casing has been sealed So this hole is pretty effectively sealed off into the top of the rock with a casing, although there's a bit of seepage that's being removed by the pump so that the bearing surface can be inspected visually. This is too much seepage for freefall concrete placement. The hole would need to be flooded to control this inflow and concrete placed with a trimming, but they were able to pump it down so that you could look at the surface. This photo shows a close-up view of the cuttings resulting from the percussion drilling of this granitic rock. It may actually have been a quartz diorite, which is similar to granite but with a higher quartz content. Another system that uses circulating fluids is the full-face rotary reverse circulation drilling with the tool that you see here. The drill is attached to a conductor pipe with borehole centralizers to keep it centered in the hole, and the drill head in blue on the right side of the photo is at the bottom of the hole. The cutters consist of roller bits with carbide buttons, which are used in this case to cut a sedimentary rock at a site in Massachusetts. The hole must be filled with fluid, typically water, and cuttings are removed with an airlift pump system that lifts the cuttings at the point of the pipe opening. The crowd is provided only by the weight of the drill system, but you can see that some extra weight has been added to the drill string to help put a little bit more down crowd on the roller bits. Here's a closer view of the cutting head. You can see how the rollers extend a short distance outside the body of the drill to provide clearance around the drill, and how the airlift pump opening is off center so that as the drill rotates, the pump rotates around the face as the cutter head turns and sucks the cuttings off of the bottom of the hole. So here's a view of the drill being inserted into the hole, which includes a casing extending down to firm embedment in a stable layer. This system can only be utilized in a stable hole. The top drive is mounted on this casing and twists the drill using the conductor pipe, which also incorporates the airlift pump system and conveys the cuttings from the drill head. The cuttings return through the swivel head connected to the top of the drill string and are conveyed to a spoil container. So here's a video that demonstrates the use of this system, which was employed on the Fore River Bridge project in Massachusetts. Foundations for this replacement bridge extended to about 180 feet below the surface of the water. So it's probably 200 feet below the top of the casing. And the reverse circulation drilling was used because the holes were so deep. This casing was advanced through alluvial sands and gravel and glacial till, the top of rock, about 150 to 160 feet below the water, using a vibratory hammer, and then cleaned out using a grab. The holes were then advanced about 20 to 25 feet into the argillite bedrock. Argillite is a sedimentary rock formed mostly of clay, also commonly called a mudstone. You can see how the cuttings are conveyed to the container from the discharge line. There's no direct discharge into the river in Massachusetts like we saw in the Mississippi River. This is a photo of the spoil container, and here's what the cuttings look like. The objective is to get the rock to break out in chips and not just grind it into flour. This is another interesting case history of the use of reverse circulation drilling. A cutoff wall was constructed through the Wolf Creek Dam in southern Kentucky using a secant pile wall with 54-inch diameter, that's 1.4 meter, drilled shafts to depths of up to 275 feet, that's 84 meters, below the working surface. The karstic limestone beneath the dam posed a severe threat to the stability of the dam itself because of all the underseepage, and with potential catastrophic consequences all the way down to Nashville, Tennessee, a major city downstream of this dam. This project successfully cut off the seepage through the limestone, and the construction of these deep drilled shafts is an interesting example of a novel application of drilled shafts and a good use of reverse circulation drilling. You can see the drill operating here and several sections of conductor pipe with centralizers just to the right. The water drilling fluid and cuttings are conveyed to this processing plant atop the spoils container. This plant contains some screens to separate the different sized particles of limestone cuttings. You can see here the limestone chips falling off the screen. I'm not sure what they did with this material, but it would make a nice crushed stone aggregate for fill or road bed or something. Certainly doesn't have to be disposed like a spoil waste product. You might wonder how you could drill secant piles to such depth and maintain an alignment so that they overlap and form an effective cutoff wall. Well, the key was the use of a pilot hole that was installed using a directional drill, technology that has been adapted from oil field drilling. One of these small diameter holes was installed at each secant pile location, being careful to steer the drill to establish a pilot hole in the proper position. After the pilot hole is completed, the secant pile can be constructed with the reverse circulation drill that is equipped with a stinger that you see here, which will follow the pilot hole. I took this photo of the drill head in the maintenance shed, turned it upside down so as to match the position in which it would advance down the hole. So you can see how that stinger would follow the pilot. This section on tools has illustrated the many creative and sophisticated ways to drill a hole, but it's appropriate to conclude this discussion with a very simple method that's been used for many years. On routine or smaller projects, or where the hole's not really deep, where boulders or irregular rock obstructs the advance of the excavation, hand excavation by a skilled worker can be employed to apply the drilling force exactly where it is needed. You can see this guy going down with the jackhammer to bust the boulder out. There are obviously many safety considerations that must be addressed in downhole entry, including casing for stability of the hole, fail-safe winching systems, air quality monitoring and air supply, and others that are beyond the scope of this discussion. Downhole entry, sometimes even with divers, may also be used to assist retrieval or repair of broken tooling or casing that may be stuck in the drilled shaft excavation. So in concluding all this discussion on the techniques for excavating, we've seen a lot of drill rigs and many tools used for excavating drilled shafts that provide the flexibility for drilled shaft foundations to be used in a very wide assortment of applications and sizes. However, there's much more to the construction of drilled shafts than just the selection of drilling equipment and tools. Engineers and constructors must have a good understanding of the construction techniques used to maintain stability of the excavation throughout the process. And that's the subject of our next lesson series, which I hope you will watch and enjoy.